tsunami, which is 100-year event. And but still, they didn't expect the worst scenario because there were no effective measures to withstand that high tsunami. So, if without moving the whole town to offshore, so they could do nothing but expecting the 5-meter high tsunami. And this is very bad habitat for us. So we need to conquer the bad habit to see only what we want to see. And anyway, Japanese seismic design code worked very well for this event. And a comprehensive seismic damage assumption is needed, including secondary element and furniture and equipment, and all the elements in the building, because they react to each other and can be harmful for the people. And this is another issue, though. The eco building can be a disaster-resistant building after the power consumption restriction. And for the future reference, I just introduce you the reasons of the slow recovery. Widespread low-density areas to recover, relying mainly on only regular transportation, an enormous amount of wrecks and rubble in small places, and ground loss of 200 square kilometers. And the residential areas proved to be dangerous for the future tsunamis. And all aspects of lives in the areas damaged heavily, all at once. And little information who needed what. And not enough stock of the materials there because of the just-in-time system, which is Toyota system. But we need to learn, and after learning from this old situation, thanks to your kind support, we will sure able to recover our site, our district. Thank you very much.
So next we'll have Professor Sasaki, his structural report on Sendai Mediatek.
I am Mr. Sasaki. I am not familiar with English conversation, so my staff, Hiraiwa, assist me. Thank you for inviting me to make presentation of Sendai Mediatek. When I received email about Sendai from Ms. Shoboji-san and AIA, I was so pleased to know many people in the United States also love and worried about Sendai, my special work. After the earthquake, because of partial interior damage, Sendai Mediatek was closed for a while, and on 3rd May, except for 7th floor, the use of Sendai is resumed. The 2011 Tohoku earthquake, officially named the Great East Japan Earthquake, was a magnitude 9.0 undersea mega thrust earthquake off the coast of Japan. It was the most powerful known earthquake to have hit Japan and one of the 5 most powerful earthquakes in the world overall since modern record keeping began in 1900. The nearest major city to the quake was Sendai in Miyagi Prefecture on the main island of Honshu, 81 miles away, and quake occurred 232 miles from Tokyo. The strong ground motion registered as a maximum of 7 on the Japanese seismic intensity scale, shortly JMA scale, in Kurihara, Miyagi Prefecture. This prefecture recorded 6 on the JMA scale and recorded 5, even in Tokyo. The earthquake resulted in a major tsunami, which brought destruction along the Pacific coastline of Japan's northern island and resulted in the loss of thousands of lives. Investigated tsunami height is up to 128 feet, and in some cases they are traveling up to 6 miles inland. These images are an excerpt from Japanese Architecture magazine, a building of Tohoku University in Sendai. The columns are broken by applying pressure caused by overturning moment of shear wall. This is a major example of building which are structurally and extensively affected by the earthquake. Fortunately, while there are some damages on interior materials, no structural damage occurred in Sendai Mediatek. The structural system and earthquake resisting system of Sendai is briefly discussed below. In order to make structural members as transparent as possible, delicate as possible, the so-called tubes were each given a dispersed three-dimensional structure with relatively thin steel frame members. The tubes are 13 separate shafts of different sizes with diameter ranging from 2 to 9 meters. The 4 main tubes with large diameter work seismically as upright cantilevers. These compose a ductile type rigid frame structure on the basement floor and a rigid single-layer lattice structure above ground. This assures a main structure that is structurally high in strength and rigidity, while architecturally transparent, strong, and supple. These 4 main tubes are distributed in a balanced way on each floor so as to avoid generating torsion as a result of eccentricity. The other 9 small diameter tubes contribute practically nothing to the resistance of horizontal forces and are suitably arranged in plan as support for vertical loads. I was asked to make the plates as possible for a span of approximately 20 meters. I therefore used the sectionally most efficient system, a steel plate sandwich structure with a depth of 40 centimeters. Lightweight concrete of 7 centimeters depth was cast on the top and integrated with the rest of the structure by means of shear connectors. One of the outstanding features in seismic resistance design was adoption of a damage control type of design. A hysteresis damping mechanism for absorbing energy was introduced in the main structure on the basement floor. The floor framing of first floor was structurally separated from the external wall of the basement by providing support only in vertical direction and by providing lower support in the horizontal direction. This had the effect of making the basement floor the level at which seismic energy is introduced in the steel frame shaft of the main structure. The rigid lattice structure above ground was switched to a ductile type rigid frame structure in the basement floor. The ductile type rigid frame is a type of structure which is in marked contrast to lattice structure from the standpoint of seismic performance. The idea was to absorb the input seismic energy during a major earthquake at the initial level of the framework at the basement floor and to reduce the input of energy in the upper structure after the basement floor has yielded. The initial level, the first basement floor, is a three-dimensional rigid frame structure with a circular plan. Among the devices that endow this level with suitable rigidity and strength and clarify its collapse mechanisms of weak beams, the most distinctive are the penetrating beams, which have been designed to yield fast at the midpoint and incorporated in ladder-like configuration, and the cast steel pins used for the basis of column. Concentrating much of energy of plastic strain in the basement floor in this way, it keeps the upper structure in the elastic state, preventing residual deformation even in a major earthquake, and also make it possible to estimate the location and extent of damage on the basement floor. The result is a clear supple design and takes full advantage of the capacity of steel members for elastoplastic deformation. This damage control system makes a restoration possible even if a major aspect of the once-in-a-millennium category strikes and a certain amount of residual deformation result on the intended level of damage concentration, namely the basement floor. Because they have been detailed to freely rotate, the column bases can be restored to their original position by using an oil pressure jack against the basement wall. The penetrating beam, which have been deliberately designed to absorb damage, can be removed and replaced. Now, I will explain what happened on Sendai mediatheque associated with earthquake record. This figure shows a comparison of this earthquake wave with two historical waves observed in Sumitomo Building, Sendai. Every earthquake occurs off the coast of Miyagi. This fixed point observation result by Professor Motosaka in Tohoku University shows the long duration of 2001 earthquake and reflects the size of large magnitude of this quake. The Sendai mediatheque located close to Sumitomo Building and stands on the same bedrock. It is speculated that Sendai mediatheque receives almost the same seismic wave with Sumitomo. Through eigenvalue analysis of building, a natural peak rate of Sendai is about 1.4 seconds. If type B, a conventional type, had been adopted, natural period would have been 1.0 seconds. The difference of natural period has a relationship with input seismic load. This figure shows a velocity response spectrum of former 3 earthquakes. Every spectrum has a similar shape to each other. Where there is a peak around 1.0 second, the value around 1.2 second are comparatively small. This means the Sendai mediatheque is subjected to relatively small seismic load by earthquake, which occur off the coast of Miyagi. And history record shows us the earthquake occur every 30 or 40 years. This fact is very important for seismic design of Sendai mediatheque. If I have adopted a conventional system for first floor, I mean type B, a natural period of building would have been approximately 1.0 seconds. This means